I am Jim. First fact. I'm also a little bit surprised and pleased that you would find your way to a session called A Little Graph Theory for the Busy Developer. It's a session that I didn't expect to be at all attended. I thought I'd have kind of a cruisy hour and a half. So fair play to you. You braved the title. That's the first good step. So I'm Jim. I work at Neartech with the guys behind the Near4j database. Who knows Near4j? Not enough. Ian barely raised his arm there, and he works on Near4j. So Near4j is a graph database. I'm going to talk a little bit about graph databases because I think they're pretty important. I think they're quite becoming increasingly important parts of our tech arsenal for storing and querying interconnected data. But actually, a lot of in this session, I'm just going to talk about graph theory and analytics. It turns out there's this branch of mathematics, computer science, sociology, anthropology called graph theory, and it's amazing. I thought, honestly, working on Near4j is a very computer sciencey thing. You know, we get to talk about quite macho things like data structures and big O notation, and we asynchronous I/O, and we get, we thought, actually, that's absolute bee's knees. This is where it's at, and whatever the users do, that's just up there and use them and blah blah blah. But about a year and a half, maybe 2 years ago now, I saw a bloke called James Fowler, who's a physician, but a public health physician, and he's been plotting the way pathogens spread through communities. That's quite fascinating. So I watched his talk, and the analytics that he was doing blew me away because he was using graphs as a model for how pathogens spread through families and communities and towns and cities. And some of the conclusions that the data was coming up with just blew me away. For example, he said, if you want your kids' friends to be thin, you should be thin. But if you want your kids to be thin, you should get their friends' parents to be thin. That is, obesity spreads at depth 2 in the network. And that you've all got the correct eyebrows now, which is like, no. Parents eat only Mars bars, kids eat only Mars bars, big parents, big kids. Apparently not. That's what I think. That's the way that intuitively I thought of it, but it's not. And so all these little gems kept coming up. That's fucking amazing. And the data was showing us things that were counterintuitive, but actually happening in reality. And it blew me away, and it kind of twisted my perception a little bit. So I was, and still am, of course, fascinated by the kind of geeky computer science stuff that we do when we're building a database. It's really quite a computer sciencey thing to do. But I got into this kind of like, this graph analytics stuff and seeing just how profound and useful the graph data structure is when it comes to analysing retrospectively and predicting how in that case, populations will change or pathogens will change, but more generally predicting how data will evolve. That's astounding. And I just want to talk about that because it really blew me away, and I'd like to share some of that with you. So, brilliant start. I just need to reboot. Hey, here we go. So, I want to talk a little bit about imprisoned data models. There's a bit of a revolution going on in the database space, and you guys have heard of the NoSQL thing, right? Yeah, lots of nodding heads, brilliant stuff. And I think there's some interesting data models that have emerged to tackle some of the perceived and some of the very real limitations of the relational model, which has held sway over the last 30 or 40 years or so. And I want to have a look in that because it's, wow. Near4j. Guess who was typing slides at the last minute? So I'll look at that because these data models, they're not all equal. They're all different and have different uses and different drawbacks. I then want to look at Near4j's data model. I introduced the notion of a labeled property graph for you. Not because necessarily I want to teach Near4j. If you want to learn Near4j, Ian and I were doing a tutorial yesterday, so you're only 24 hours late before that. But that tutorial is online, and you can still download it and work on it. In fact, there is Near4j online training, which you can go to at near4j.org and get to grips with Near4j. So I don't want to teach you too much about Near4j. I want to introduce you to a property graph model, because I want to use that property graph model to do some graph theory stuff. And I want to look at two things which are pertinent, I think, for where we are at the moment. I want to look at South East London, which is where I live. It's the kind of stabby part of London. I live between, get this, my neighbourhood is sandwiched in between Brixton and Peckham. So I'm about to pick up here. South East London as an example, and also it's the 100th anniversary of the outbreak of World War I, which is a terrible thing for our species. But I want to demonstrate that graph theory actually could have accurately predicted the beginning of that conflict based on a starting point of the great houses of Europe during the 1800s. So I think that's an eerie and amazing and equally very saddening thing that this abstract mathematical problem-solving tool can predict very, very tragic consequences for the human race. So that's a kind of yay and, but yeah, anyway, kind of yes, nice and horrible at the same time. And then I'm going to flip it round. So this stuff around stabby South East London and World War I is about predicting using graph theory. I then want to flip it around and do some retrospective analytics with graphs. And there's one of the first things that, second thing actually, that Ian and I did years ago, before we worked on Neo4j, when we were software consultants. The second thing we ever used Neo4j for was retail recommendations. So I want to tell you about how you can use graphs to make extremely accurate, up-to-the-moment recommendations. I'll pick retail because it's a domain we're all familiar with, but recommendations across pretty much any domain. And then I'll actually demonstrate that for real. I'm going to show you how you can build something like the dunnhumby Tesco loyalty card scheme, which they've taken 20 years and zillions of pounds to build, in about 3 minutes on top Neo4j. The data set might be a little bit smaller, but the techniques that we'll see are very, very similar and very expressive and powerful. And put Q&A in, but I'm sort of happy to take a bit of answer a few questions as we go along. It's a reasonably small room, you can all yell, right? Anyone want to practice yelling? No? Okay. No. All right, cool. Anyway, I'm going to say some things that are going to be a little bit challenging or inaccurate or intellectually dishonest that you should probably yell about those. Keep me honest. All right, so we've all been here, right? This is the last 30 years of our lives for some of us. And it's like schlepping through the join of the outer left, upside down, topsy-turvy, right join of blur, through 17 different fucking tables, just to change this flag from true to false. There is a man who is defeated by this. You should have seen this solemn nod of the head. Sorry, bro, I mean, stay strong, man, stay strong. We'll bail you out with graphs shortly, but until then, stay strong. You watch it. If he goes for his wrists, you let us know. Tables, meh. Tables are great for some things, right? Tables particularly were great for some things back in the day when everything was boringly uniform, when we were all square, when we all had the same work payroll system, when we all had the same medical records. In fact, when we had an NHS, for example, these bastards sold it off. Anyway, politics there. I always find myself becoming more political when I'm going to talk in Westminster. Just hope that like some osmosis, my kind of like lefty angst will propagate over there and cause one of them to stumble and fall down the stairwell. Anyway, so we've been there in the relational database world. Okay, now I'm looking for the people who are IT people are generally sensible, so we'll go. I'll pretend you're all a bunch of lefties. So we've been in this world, and it served us okay, but it's not suitable for everything. And one of the things that relational databases handle very poorly, and that's actually data at large volumes. They're fine with data at large volumes, but right up until the point you have to join. So relational databases run like the blazes until you have to join. And I don't care how good you are at relational database schema design, I don't care how good you are at SQL query design, at some point you're going to join. And that first join, you considered it carefully, you know there aren't going to be crazy indeterminate sets produced, and you go ahead and join and your query runs and you're like, yeah, suck that up, SQL Server, I own you. And then you put a second join in and you're a bit more nervous, you're a bit less cocky, you're like, please work SQL Server. And it maybe works in a few seconds. And you put the third join in and all bets are off, right? So you've got this join one problem in SQL databases, particularly as data set size grows. Not a criticism of SQL databases per se, but the underlying mathematical model is set theory. And you're doing unions of sets, Cartesian products of sets, in order to build up a superset of building answers and then filtering down to get the results you actually want. That's okay, except when the data set's big, because then you have indeterminacy in terms of memory use, indeterminacy in terms of query latency, and then you get some like voodoo guy into Oracle or Microsoft to kind of fine-tune your queries and push even more licenses on you for more instances of SQL Server. You know the pain, right? Yeah. It's not good. So what happens? So a bunch of disparate database vendors kind of clubbed together under this brand NoSQL, right? So it's actually several different kinds of database on there. And I think that's really fascinating because up until about 2005, when you chose a database, you were actually choosing a brand. You weren't choosing a database. You were like, do I want exactly the same thing from Oracle, or exactly the same thing from Microsoft, or exactly the same thing from IBM? You weren't choosing a data model. The data model was a foregone conclusion. We even have the symbol for it in Visio, right? It's not like Visio now has a NoSQL symbol, is it? Always the round thing, the round spinny cylinder, relational database. The NoSQL guys came along and said, well, look, for some problems, the relational database is not at all sufficient. And so we want to offer different data models, primarily focused on dealing with large data sets. And the first of these data models is the key value stores. So the data model with these things is a big hash map. If you've got a key, you can store and retrieve a value. And these things are really good for things like shopping carts. In fact, one of the most prominent early key value stores was exactly that. It was Amazon who built a database called Dynamo. And Dynamo was the database they used for shopping carts. And they were very, very, very concerned that you should always be able to add to your shopping cart. And that database should be non-stop. And of course, the shopping cart's a very simple structure to keep the value. They didn't get any benefit, it turns out, from a lot of the modern richness and constraints and schema and so on that the relational database at the time were offering them. And this is actually, it's really weird now. We take this for granted. Amazon built a NoSQL store. Think of it this way, 2005. How many of you guys in 2005 were building alternative databases? One day someone's going to put their hand up and it'll be like, someone from Amazon or Google or something. No, you weren't. No one ever walked up to their project wall, picked up a card, they looked at two cards, like this one's like CSS, make the buttons round here, or invent a entirely new kind of database for non-stop shopping. I'll say that one. Right? No one was doing that. Everyone was using SQL databases and we were pushing them hard to their limits. Amazon looked at the value proposition of SQL database, particularly around modeling and schemas and constraints and so on, and actually, we don't need that. It gets in the way of our primary goal, which is large volume of shopping carts always available. So they built Dynamo. And of course, this pedigree then went forward into other NoSQL databases like React and Aerospike and those kind of things. And they're available now as kind of commodity technology for us all to use. The next part of the family of NoSQL databases are the column stores, as exemplified by Apache Cassandra and HBase and so on. And the provenance of these guys is Google's Bigtable. And it's a pretty similar data model to the original key value stores, except it's a nested hash map of hash maps. So it's kind of a more multi-dimensional kind of notion. But what's lovely, I think, about column stores is, as the keys line up in those nested hash maps of hash maps, you get natural index emerging from them, which gives you a bit more insight into your data than just a plain key value store. I think that's lovely. They tend to share, Cassandra, for example, tends to share great operational characteristics, tends to be very highly available, very scalable and so on when you queue it. HBase is making a bit of a comeback, which is great. But the intelligentsia, the digital intelligentsia debate back and forth about which is the most stable or scalable actually of the column stores. Is it HBase? Is it Cassandra? Is it this thing that I just hacked up and put on GitHub over the weekend? Of course, we in this city know which is the most scalable column store. It's this. This is the British Museum. It's where we store all the stuff that we nicked. It has columns. And when we need to expand it, we just build another wing to store all the other stuff that we need. So there you go. Now you know the answer. Then there are the document stores. Has anyone ever Googled MongoDB is web scale? Does anyone, serious question, is anyone thinking about leaving IT? Is anyone a little bit disillusioned? That's true. If there was someone that's secretly disillusioned about IT and is just looking for the final nail in the coffin to leave, please Google the phrase MongoDB is web scale and watch this cartoon. Anyway, Suffice it to say, MongoDB is a very successful example of a document database. And the document database is things like CouchDB, MongoDB, and so on. I think they have the most straightforward and immediately familiar kind of data model to us. It's store a document, retrieve a document. It's a filing cabinet metaphor. Store a document, retrieve a document, or index a document. I mean, equivalent to putting your filing labels in your cabinet. If you've ever used a source code control system, then this metaphor of document is immediately familiar to you. What's interesting about key value stores, about column stores, and about document stores is actually they're very similar in a way. So there's this chappie called Martin Fowler who wrote a book with a guy called Promote Sadlich called NoSQL Distilled. It's a really good book actually. It's genuinely straightforward, comprehensive, and down to earth book to read. And in that book, Fowler and Sadlich observed that key value, document, and column stores are all aggregate oriented. That is, they work well when you store and retrieve symmetrically. If you store a shopping basket and retrieve a shopping basket, that works really well. If you store a person document and retrieve a person document, that works pretty well too. But if you store a person document and then somehow you want to slice it and dice it with some trending, what's selling, product sales kind of data, those databases tend not to be brilliant at that. Which is odd because your SQL database can answer those kind of questions. So what you do when you've got an aggregate database, you want to join things together, if you want to split the data, if you want to analyze the data in a way which isn't symmetric with the storage and retrieval pattern, well, typically you jailbreak it. You drag the data out of the database, you run it through some processing infrastructure like Apache Hadoop, that grinds around your data, and then you get some insight, you get some information back. And if you're sensible, you'll push that back into the database to close the circle. But it's a bit abrupt, right? I mean, data loves being in databases. It's just all safe and warm. It's like swimming around in the amniotic fluid of the database kernel. It's lovely in there. Data doesn't like being dragged out and pushed through the sausage machine. That's my sausage machine impression. Sometimes it works for people. And then they kind of finally get their answer out, and that's fine. It has the drawback that it's potentially fragile because you're taking data out where it wants to be. It has a drawback that it's typically very latent. It's a very compute-centric model rather than a query-centric model. And of course, even those relational databases have a query-centric model. I think that's interesting because these guys have all tried to tackle complexity in a very one-dimensional way. Complexity for the majority of those SQL databases is size. That's the thing where relational databases fall over. That's the thing that we must tackle. But complexity isn't just a function of size. Complexity is a function of how uniform or disuniform the data is. And importantly, complexity is a function of how interconnected that data is. Think about something like the Facebook data set. What makes that interesting? Is it the fact that you are all nodes in the Facebook graph? No. Facebook make their money by exploiting the connections between us. Not us. We're just raw material. It's the connections between us that enables Facebook to make that gazillion-dollar business. So connectedness, I think, is key in tackling complexity. And so we're faced, really, in the NoSQL world, with a very bifurcated decision. Very bipolar decision, actually. We can take the left fork in the road, and we can choose to denormalize our data into aggregates, into keys and values, into columns or documents. And then when we want to get insight across sets of documents, or slice and dice them in some interesting way, we can adopt a compute-centric approach. Take the data out, compute across it with MapReduce, and then store the results back in. Or we can take the right fork in the road, where we don't denormalize, where we have a richer data model, we have a connected data structure model. And instead of computing data, dragging data out and computing it, we're actually going to build a high-fidelity model, and we're going to query it. We're going to build a model and ask it questions, which is actually what we do with SQL databases, right? We build a model and we ask it questions, and that's the way we gain insight. In fact, this is the way we're going to go with graphs and graph databases. We're going to take this form. We're going to build a rich model that looks like our domain, that's high fidelity, that is not lossy. And we're going to traverse that graph, we're going to crawl around that graph, looking for information goals. So this is a graph. It's a graph that, who are you native Londoners who live in London? All right, you're not allowed to answer this question. Who are you, after the rest of you, I'm going to assume are out of towners. Recognize the graph? Yeah, it's a graph of the London Tube network. Do you guys, given this graph, think you can navigate the Tube network? Yeah, of course you can. That's interesting. That means immediately graphs are visually accessible, they resonate with us. If I'd given you this in tabular format, would it be as useful? No fucking way. You'd be like, why would you print the tube map in CSV? That is cool and unusual and just useless. You bozo. But as a visualized, as a connected graph, it gives us some information. For example, I know that if I'm here at, say, Chancery Lane, I know that I can't magically hop to Farringdon. Why? Because there's no link. I can get to Farringdon, where I have to go round here, round here, round here, down, down, and then I get to Farringdon, right? So it also tells us, when we're at a particular station, or node as we call them in our model, I know the legal stations I can hop to next. So each station is actually acting as like a little index about where you want to go next, which is interesting because when you build a computer sciencey version of this, you can take advantage of that to make it ridiculously fast. No global indexes, you don't need them. You've got this adjacency-free indexing property. So, for those of you who don't live in London, the Neo4j office is down here. This is London Bridge. We are just across here a bit from London Bridge, and of course we're over here in Westminster. If I was going to go, and I do need to do this tonight, if I'm going to go from London Bridge to Paddington, so I can get on the Heathrow Express to Heathrow and catch an aeroplane, what route would I take on the tube network to do that? And there's always someone to say, take a cab, but I'm a starter, and London cabs cost like £400 a mile, so that's not happening. What route might I take? Someone else who doesn't know the correct answer. I need to be able to mock someone before I can accept the correct answer. So I might say, oh, well, look, what I'll do is I'll take the northern line to the yellow and green line, and go on the yellow and green line down here, and then up here, and then I'm at Paddington. Right? And that is actually a legal route. Although, if you took the tube this morning, you'll know that the district and circle lines are having a major, major meltdown. What does that mean in graph terms? It means it's a high-cost path. Right? It's quite a long path. It's going to cost me many, many minutes to take that route. Someone uttered Jubilee. I probably would. In fact, I think a shorter cost is to go a bit south, take the Jubilee line up to here, and then change and cross over to Baker Street that way on the Bakerloo line. Actually, having worked, I live obviously down in Stabby, South East London, and I've worked out west. So I've done this about 200 times in my life, and that's definitely the best route I've empirically determined. Apart from when you get American tourists with big bags going to Heathrow peak hour on the tube. If that's you, no one in the city likes you. You are that guy, and you are not loved. Anyway, so graphs are awesome because they enable us to pick our way through what is a very complex network topology to achieve a goal simply. And in fact, Mark Needham, one of our colleagues, has kind of figured this out. It's like, graphs are awesome, but there's a bit of a learning curve. And we all start, particularly with Neo4j, we're like, oh, this is really hard. Like, where are my tables, where are my schemas, how do I do my first normal form, and all that stuff that we've been so trained to kind of believe is how you do data goes out the window. But once you get over this hump, you find actually graphs are awesome. Graphs are very simple to model with, and there's no baggage, there's no overhead, there's no ceremony with them. You draw a graph on a whiteboard. If it reads correctly, typically that's ready to store. What you draw is typically what you store. There's no, okay, we've just gone to third normal form, but now we need to sacrifice a chicken to Larry Ellison and denormalize it, blah, blah, blah. No, draw it on the whiteboard, that's what's going in the database, which is great. So, now that we know a little bit about graphs, we can meet this dude. This is Leonard Euler, who's a Swiss mathematician, inventor of graph theory 275, 276 years ago. And he is to us in computer science what William Shakespeare is to students of literature, which is like some old geezer who's put in our computer courses to make them even harder and more dull than we could possibly imagine. Or at least that's what I thought when I was an undergraduate. I now regret that, since I'm chief scientist at a graph database company. That's a little name over there that we can share. And it won't leave the room, that video will be edited. And what's Leonard up to then? So Len is kicking around Königsberg, now Kaliningrad, and the River Pregel flows through Königsberg. And there's a teaser, which is it possible to cross all 7 bridges over the River Pregel without retracing the steps? That is, crossing each bridge once and only once. And generations of empiricists have kind of tried to do this, and by empiricists I mean idiots that were kind of schlepped around. I know I've been on this bridge before, start again. And Len, as I like to call him, Lenny, more South London Len. I don't know if I do that when I go to South London. It's like particularly now I've got like a handled implement in South London. I think in British Standard Sign, that is the sign for South London. Anyway, Lenny is kicking around Coningsburg and he's like, no, I'm not a mug. See, I've got all the South London words coming out now. I'm not a mug. I grew up in Birmingham, so this is anyway, I'm not a mug. I'm not walking around this city. I'm going to invent an entirely new branch of mathematics because I'm lazy. So he does, and his brilliant observation is, actually, much of the problem domain, that it's bridges and cities and rivers, is irrelevant. What we actually have are land masses connected together. And in fact, you can go a step further and say it doesn't even matter that they're land masses. They're just things connected to other things. And that's an amazing observation, because that's what you do for your job, right? You have some guy or girl who comes up to you and they call product owner or scrum master or some job like that. And they come up to you and they blather this barely coherent nonsense at you, which is apparently a requirement. And you're like, all right. So you sit and you kind of let it filter through and you're like, right, make the buttons round here. Okay, that's all he wants. But anyway, they give you this kind of real world description. This real world description is often full of noise because people are shit at writing requirements. As software engineers and developers, our major skill, I think, is not just in the kind of typist kind of domain, but it's in understanding real world requirements and thinking, yeah, that doesn't matter, that's the key. And that's what we do. We take the real world requirements and we break it down to a logical model. Right, so we kind of pare out all of the noise and chaff, and we produce a design. Yeah, we might express that design in terms of unit tests, for example, or if you're old school, some kind of like verbose, useless UML document. Sorry, any architects in the room? Oh! Now, I should have said, anyone want to identify themselves for the next 10 minutes of banter? Okay, great, you're a good sport. I'm kidding. And then we take that logical description of the problem, and we turn it into an executable specification, which we call software, right? And that's what Leonard Euler was doing. Took the messy real-world problem, turned it into a logical description of the real-world problem, and then turned it into an executable specification, which today we know as graph theory. And in fact, no, you cannot walk around all 7 bridges in Königsberg without retracing your steps, proven by Euler's graph theory. And so this gave birth to this wonderful thing. Yeah, let me hang on a little bit there, boys and girls. This is a graph, and this forms the basis of a bunch of amazing analytical things we can do. This is a graph. This is an interest graph. This is a graph. It's a graph of people who communicate via Facebook across the world. In fact, the graph is so interesting that it's so densely connected around the user base. You can see kind of countries emerging from it, which is fantastic. This is a graph of US internet connectivity back in the day. This is a graph of something to do with physics that I do not understand. But it's in there because it's a graph. This is not a graph. This is a chart. Percentage of devs that love Neo4j in 2014 is very, very high, you sensible developers here. So, okay, graphs. Graph structure, things that are connected to other things. Can't my relational database already do this? Because I know a clever SQL guy, and it's always a clever SQL guy. The ladies don't get embroiled in this. It's always some guy with like halitosis and like bad attitude, and he'll never let you change the schema, but he reckons he can already do graphs in his SQL. Because there's a book about it. There's a book called in fact, what's it called? Trees and Hierarchies in SQL for Smarties. I would like to, at this point, just say one thing: fuck you, DBAs. Because that is just outrageous. That most books are at least for dummies, for normal people. No, fuck you. You have to be a smarty to do this. And I think that's really disenfranchising, because I'm not a smarty, so I feel left out in the cold by this stuff, right? I want to do this in a more kind of friendly way, and we will get to that. So, you've got a SQL database, and you might have, in this case, representing customers who hold multiple accounts. And in the middle of this, you can see this, because this is pretty simple, right? I mean, you can imagine the real schemas that you work on are far more horrible than this. So we've got Alice over here, who owns, in this case, 3 accounts, and we might want to, do some joins across these tables so that we can get Alice's total position, whether she's in the red or in the black. But actually, so much of this, particularly this bit in the middle, When I first learned databases, like when I was a kid, I couldn't believe that the relational database wouldn't build this one for me. I was desperately disappointed. I was like, no, Access should do this because it is obvious what my intent is, and it isn't. And I got really pissed off that the database doesn't really do this for me. It's like, well, what do you do? I tell you have to do everything, and then all you do is complain at runtime that my SQL isn't optimized enough. Anyway, there's this thing in the middle, this join table, and this is a simple join table, but I guess most of you in this room have seen the database schema where there is the join table. It's a 2 or 3 column table, and it joins everything to everything through everything. And there are recursive SQL queries that are the very pit of despair and insanity that goes through that table. And it's not nice, and the queries are unpredictable and so on. This thing is a bad thing. But it'd be nice if it was gone, right? I don't really care so much about that table. What I care about is that Alice owns accounts. That seems more important. It seems much truer to my domain that Alice owns accounts. And if I can get rid of all those other rows as well, now I've just got Alice with accounts. That seems nice. That seems kind of like a more humane data model. Alice owns accounts. Sure, in fact, now I could label them. Alice is a customer, Alice owns these things called accounts. She has 3 of them. Where is the clutter? Where is the denormalization? Where is the opportunity for an Oracle DBA to eke a living? Not in this one. And so this is the model we have. We have nodes that represent entities in our domain. We have relationships which link those entities together. Relationships are directed and named. And then we have labels which kind of tag or taxonomize things in our domain. They separate customers from cars, from buildings, from bank accounts, and so on. And this is a lovely model because it's really simple. I'll prove it to you. This label property graph model can be concisely described as follows. We have nodes which can have properties on them. Properties are just keys and values. And optional labels, so we can tag them with a kind of taxonomizing tag. Relationships are directed, they're named, and they can also have properties on them. And they must have one start node and one end node, which must be the same node. That's it. That's the entire data model. Do you remember the relational databases book you had at university? That thick? Okay, I don't know how thick ebooks are nowadays, but that thick is how I remember it, impenetrable and horrible. That's the data model for Neo4j. Now, the true reason behind all this is so that Ian and I, the only reason we do all this is so that Ian and I can maintain a Doctor Who data set going back to 1963. But I'd like to share it with you because it teaches you 2 things, Doctor Who and graphs. So, here is a node. In fact, it's Matt Smith playing the almost most recent Doctor. Now we can draw the simplest graph possible, 2 nodes, 1 relationship. This is the Doctor, this is a relationship marked from, and it's directed, and this represents the planet Gallifrey. So what does this say? Doctor from Gallifrey. It's not Gallifrey from Doctor, that doesn't make any sense. But now we've created a graph. We've created a simple graph of 2 nodes. You guys are with this, right? I mean, this is Doctor Who, this is... I'm not going to have to explain to anyone what a Dalek is, right? Okay, I do that now and again, and I've got to admit it's a little bit soul-destroying. Okay. We're going to go with this. So the Doctor, you know, the Gallifreyans, the Time Lords actually have invented the ability to travel in time and space, but they can't be arsed. They'd much rather just sit around watching the universe go to pot. They're kind of like, yeah, whatever. The younger races can do what they want. The Doctor's a bit more impetuous. He's like, yeah, I want to get out into the universe. I want to kind of, traveling and see the place. So he steals this thing, his time machine, his TARDIS. In fact, if you've seen some of the more recent Doctor Who, you could argue that the TARDIS stole him as well, which was a brilliant episode. Brilliant episode. So the Doctor nicks this time machine, goes barreling off into the universe, and starts putting right things that are going wrong. And in doing so, he starts to make enemies. He becomes an enemy of the Daleks, an enemy of the Cybermen, an enemy of the Sontarans. This is Ian Robinson's slide. He put the Sontarans in because he says I look like one. Because he knew I'd Robin, because my slides are rubbish. Anyway, so you've got, this is kind of an anti-social network here that the Doctor has kind of formed, like all the enemies that he's battled. And then, of course, the Doctor's quite a needy guy, right? He often travels with companions, and his companions are often humanoid because the BBC wardrobe budget is tiny. And until recently, he was travelling with these guys. This is Amy, and this is Rory. And Amy and Rory have their own side story. In fact, they're in love. Amy loves Rory, Rory loves Amy. Notice, this is not unrequited love. If this relationship didn't exist, yeah, we've all been there. You know, you like them more than they like you. We computer people, for heaven's sake. It's our normal state, isn't it, really? having a bit of a crush on a norm, and then they don't see you, and unless they want you to read, unless they want you to fix their email or whatever, their Twitter, whatever norms do, normal lives. Anyway, this is lovely. This is a social network. In fact, this is the starting model for building your own eharmony.com, whatever. But then, of course, there's the real world of Doctor Who. Right? And the real world of Doctor Who, I'm not a nutter, right? I don't believe Doctor Who actually exists. The real world of Doctor Who are the episodes that the BBC package for us. And those episodes are kind of like a focal point where the mythology of the Doctor Who universe meets the real world, where, in these episodes we bring the Doctor and the Daleks and Cybermen and all that together with actors and producers and directors and the guy who makes the bacon butties and the coffee. And so there's a whole real-world supply chain that comes into that, and quarries in the Midlands feature heavily in some of this real-world stuff. And that's the wonderful, wonderful thing about graphs. You can take arbitrary dimensions of data, put them in the graph, and bring as many or as few of them as you like together when you want to query them. So if you want to just query the Doctor Who universe for, in which episode did Amy battle the Daleks, well, you look for episodes where the Daleks appeared in and Amy appeared in. You say, well, that's a candidate. But you could equally say, in which episode did David Tennant eat a bacon butty while filming in a quarry with a Dalek? Bringing in some of that mythical stuff. Yeah, we could actually answer that. So. Near Jane, you can bring in all these mixed dimensions of data. Of course, in a real world, proper, kind of non-cheeky data set, you can actually bring in arbitrary dimensions of data as well. You don't have to be afraid of pouring facts into your database. It's not going to hamper you at runtime. And finally, of course, we can label these things so we give a clue as to what their role is within the network, more so than simply what the structure provides. So that's the graph model. I now want to look at doing some analytics with graphs. And I want to start off with South East London. This is my local high street. I live in East Dulwich, which is, it's a bit posher than Peckham and Brixton, right? I can't lie, but it's not terribly stabby. I've only been blown all once. What tickled me when I saw this blown up large for the first time was this shop sounds, it's not a good shop actually, it's like an off-license. And it sells Turkish, Greek and Mediterranean food. But if you're in the mood for something especially bland, it also serves English food. That's genius, that is, right? Yeah. That stuff all looks delicious and Mediterranean, but I'll take the blandest thing in the delicatessen, please. Yeah, English food. Anyway, so why this? There's a notion of graphs of local properties, and local properties are upside down. It turns out in the graph, it's not the things that happen at big scale that are important, but it's the things that happen at the micro scale that are important. And the things that happen at the kind of local scale, these local properties, profoundly influence how the graph grows as a whole. And the easiest one, the most basic one, and actually one of the most powerful, is this notion of triadic closure. Now, why is it called triadic closure? It's because the graph theoreticians are unable to use the more humane phrase, making triangles, because it sounds childish. They are more like the Haskell programmers. You know when a Haskell programmer tries to explain the M word to you, they don't just say monads, they say monads, like Harry fucking Potter, right? And you're like, because you don't understand monads because you're a normal human being, they like lord it over you, they're like, but it's a monadic function. What does that mean, a monad? It's a monad. Anyway, I think the graph theory, I did this with Simon Peyton-Jones in the audience and Phil Wadler. Simon Peyton-Jones laughed it off, Phil Wadler walked out. It was an interesting A/B test. Anyway, so triadic closure just means to make triangles. There's a tendency in graphs, particularly graphs that involve humans, to form triangles. So this is taken from the South Park cartoon series, which is like a kind of American cartoon series set around an elementary school, which I guess is like a primary school here. And we've got three young boys here. This is Kyle and Stan and Kenny. And Kyle is Stan's friend and Kyle is Kenny's friend. And you can see the tension here, right? If Kyle likes Stan and he likes Kenny, at some point it's very likely that Kenny and Stan are going to kind of get to know each other. And you can see that in your real life. If you've got a couple of mates, because they're both mates with you, they're probably going to get introduced, and there's a good chance because they can be compatible with you, they'll be compatible with each other, they're going to become mates. So this tension is fulfilled in the graph by closing the triangle, hence triadic closure, or making triangles as more human people call it. So there's a tension that says if Kyle is friends with Stan and Kenny are going to become friends too. So that's fine. And then there's this notion of structural balance in the closure. So you can imagine now I've got a slightly less friendly situation forming here, it's slightly more antagonistic graph, where I've got this guy Cartman, who is a like angry little fat kid, who is my hero. Modulo the occasional genocide, but I don't approve of those, but generally speaking, I think we would all be better off if we lived our lives like Eric Cartman and just shoved our faces full of cheesy poofs and played a lot of Xbox. That would just be wonderful. This is why we're in computing, right? Because it's the next best thing, screwing cheesy poofs. Anyway, Cartman is a nasty piece of work, but he's friends with this guy called Craig, or he's an enemy of this guy called Tweak. In fact, there's an episode where Cartman does nothing more than stir it up between these guys, and he's all like, hey Craig, Tweak's such a douchebag. And well, I can't do Craig, but Craig's like, no, you know, whatever. And so one of the ways we can close this triangle would be for Cartman to be a friend of Craig, Cartman to be an enemy of Tweak, and for Craig and Tweak to be friends. It's close the triangle. But that feels awkward, right? Because now when Cartman is bad-mouthing Craig, bad-mouthing Tweak to Craig, it's like, you know, Tweak's horrible, why don't you have a fight with him? Craig's like, well, actually, no, Cartman, Tweak's my friend. This feels awkward, right? I mean, you get down the pub yourself, if you're playing the card and all, it's just bad form to badmouth someone who's like a friend of your friend, even if you hate them. It's an awkward triangle. It's not structurally balanced. There's a tension there. There is a structurally balanced triangle, however, if we have two enemy relationships. So if Cartman hates Tweak and Craig hates Tweak, that's balanced. It's not a good thing, right? Because kids are bastards. But it's balanced at least because now Cartman and Craig can gang up on Tweak. That's really immoral, isn't it? I'm actually teaching like anti-ethics through the medium of graph theory, but that is a structurally balanced closure. The graph wants to get to these kind of low energy states where the triangles are in these stable configurations. Of course, there is one more stable configuration, which is where they're all friends. That's nice too, right? That's the morally better configuration, but the graph does not care. And I'll show you why. So structural balance and triadic closure, structural balance and triadic closures are a key predictive technique in graph theory. And I want to demonstrate this by stealing an example from an excellent book called Networks, Crowds and Markets by Easley and Kleinberg. It is the best book on graph theory you will get. It's brilliant. It's an academic book, it's that thick, and you think this is going to be really shit and boring. It's amazing. It's a page turner. Mixes game theory and graph theory. Buy it, read it, you'll enjoy it. The second best book you can get on graphs is Robinson and Weber's Graph Databases, of course. So here is a graph of the great houses of Europe in the middle 1800s. This is a configuration of friendships and enemy ships, which are depicted here by the black arrows are friendships or allies, and the red arrows depict enemies. And I'm very proud to say I'm pleased about that one. This is a configuration that historians call the Three Emperors League, the Austro-Hungarian, Germans and the Russians. And what we want to do now is simply iterate over this graph, making triangles, making structurally balanced triadic closures, or making stable triangles. So let's do that. Let's start to go fast forward over this. So Italy gets introduced to the graph. And here we go. So Italy now forms a stable triadic closure by being a friend of Austria and a friend of Germany. Yeah, great stuff going on there. And then Russia becomes hostile to Austria and Germany. We now have another closure formed. Fast forward again. Got it? Russia and France become allies. Now, thank you. This is, over here. This is stable. It's not good for the Brits. It's like France is like, hey, Russia, let's kill the Brits. And Russia's like, yep, we should definitely behead their monarchy and form a socialist republic or some shit like that. They're brewing at this point, right? So the French, who are, of course, the most trustworthy of our neighbours, ganged up with the Russians against us. The Russians still hate the Austrians, the French hate the Austrians, we hate the Austrians. I don't know why, man, great scheme. And almost never do they, raise their kids in the cellar. I mean, that hardly ever happens. Tantalizingly, for those of you who are members of UKIP or the EDL, notice we are not hating on the Germans at this point. Which is great. The Germans are having a reasonable kind of social revolution there, where they're starting to get a bit more kind of trade union stuff, which is great. So then we fast forward. That happens. No one expected that, right? This is the Entente Cordiale, which my schoolboy French, if I remember it correctly, the translation is, please stop killing us all the time, Britain. So I think that's how it translates, something like that. A bit of liberty, obviously, with the direct translation there. For millennia, we have been kicking these guys' asses, and they've been like writing all of them down as victories on their Arc de Triomphe. And now suddenly they're buddying up with us. This is weird. I think this is the worst thing actually, because now what happens is that forces Russia, in order to keep in order to make a structurally balanced closure, Russia has to become friends with the UK, and then as you fast forward, simply stamping out those stable triangles, you end up in this low energy state for the graph, this very stable state for the graph. Unfortunately, now you've got from a graph theory point of view, this is awesome. Look at all the nice stable quadratic closures. Every single triangle in this graph is now stable. Unfortunately, this sets the scene for the First World War, the most tragic meat grinder that humanity has ever experienced, until the Second World War. Go us! Yeah, well, we're good at this shit, right? So graph theory knows nothing about Germany being like a bunch of warmongers, or France being a bunch of wimps. He doesn't know any of that kind of detailed domain stuff. I should be a tedious. No, I should join UKIP, right? That'd be like brilliant UKIP banter. All I need is a pint of a cigarette to prove I'm a normal guy. And so, but it doesn't know. All it knows about is making these stable triangles. And what's wonderful is, just by iterating over a data set from a starting point, taking it forward, we are actually able to predict, and we know now, with hindsight, with a great degree of accuracy, how World War I started. So this, as I said, comes from a book called Networks, Crowds and Markets, and I would implore people to beg, steal, or borrow a copy of that book, because it is absolutely amazing. Triadic closures then. So strong triadic closures are also important. So triadic closures not only have sentiment, but they can also have strength. So we're seeing that we can have friend and enemy relationships, but those friends and enemies can be of varying strengths. I mean, you have really close friends and you have kind of more distant friends. So you have strength in those relationships, and those weak relationships, in the same way that the local properties are so important to the overall mutation of the graph, weak relationships are actually more important in a graph data model than strong relationships. They identify neighborhoods in the graph. So if we can find the weak relationships, we can find the neighborhoods. We can find departments in a company, like tracing email looking for those weak links. We can find terrorist cells, individual cells, because they only have weak links between them. We can look for those neighborhoods in the graph and start to exploit this local bridge property. Here in South Park Elementary, there is a local bridge. In fact, unfortunately, if you're in IT, this actually extends into your professional life, it turns out. So when you're young, you have the boys and the girls, and they don't talk to each other much, apart from like one brave soul, in this case it's Stan, who is man enough to have a girlfriend, which is Wendy. He's not super manly about it though, because every time he approaches Wendy, he gets so nervous he vomits on her, which is, as it turns out, not a brilliant way of attracting a mate for the long haul. Anyway, Wendy's kind of used to it now. But what's interesting is, any time this community wants to learn something from this community, it must travel across this weak link. That's interesting. If you project this into your real world life now, what does it mean for you? It means that your friends will not be telling you where your next job's coming from, because you already know what they know. You're embedded in this network. But if you can transit across a weak link to another community, this community knows different stuff to you. Your next job is coming from here, and it's travelling over this weak link into your community. So your friends are friends over weak links, which will tell you where your next job opportunity is coming from, not necessarily your strong and close friends, because you've all got access to the same information. Now, this local bridge property is also useful in being able to predict how graphs will evolve. And I've got another example, historical example, which I've taken from the 1978 American Journal of Anthropology. And yes, the long winter evenings do fly by in my house, in case you were wondering. And what's interesting about this club, this is a university karate club. And the node labelled 1 here was the original student president of the club. And as the club's grown, it's taken on a lot more members, more than the original student president can teach, and they've had to bring in a professional instructor as well to augment the teaching. But you can see, as humans, you can already see this kind of clumping going on here, right? And actually what happened we know from history is that eventually the club split. And some of the students went with the original student president of the club, and some of the karate students went with the new professional instructor. We can predict that with some great degree of accuracy by partitioning the graph and looking for those weak links. Now, graph partitioning, if you do it properly, is NP hard. I know this because me and my team and Ian's team in London, we work on splitting graphs across databases. It's a really damn hard problem. But there are statistical algorithms you can use which will give you this much more cheaply. Now, graph theory will predict a split as follows. All of the kind of pink shaded nodes will end up being splitting into the original student president's new club. All of the white shaded nodes will end up going with the professional instructor. And you can see this makes sense, right? Because this guy is much more embedded with these people who are embedded with this guy. There's kind of much more deep entanglement around the student president here. And there are relatively few links here, these kind of weaker links bridging neighbourhoods. And you've got the same kind of clumping going on here. And so graph theory predicts that split. What's amazing is graph theory gets it wrong. Oh my God, it predicted World War I, it can't predict a karate club. Check this out. See that? Watch node 9. That's what graph theory predicts. Predicts that node 9, student 9, will go with the professional instructor. Why? Because he's connected in a network that's much more connected to that instructor than he is to the original student president. In reality, we know in 1978 the club split this way, and student 9 stayed in the club with the original student president. Why? Because graph theory can't know that student 9 was 2 weeks away from completing his black belt underneath the original student president. It was not in his interest to leave the club. So graph theory provides an amazing way of doing predictive analytics, but it's not foolproof. It will give you a good answer, but please don't be betting money on it. Unless you want to bet with me, I will definitely be your counterparty in that bet if you promise to only use graph theory. So it gives you good predictive capability, but it's not perfect. Yes, mate?
Isn't that just because it didn't model the link properly?
No, it modeled the link. There was just some other context it didn't know. So if we were to build, the only relationship in the relationship type that we have here is kind of like knows or friend or something like that. If we piled on, kind of the academic side of things, has done, belts yellow through brown under this guy, blah blah blah, is only 2 weeks away from doing black under this guy, then I think graph theory might have made a better prediction. But I think it's a good point because you're saying with better data in, we would have got better results out. You're right. The 1978 US Journal of Anthropology did not have Neo4j on its side, so it had to do necessarily very limited graphic things. So that's predictive analytics. There's also a retrospective side of analytics, which is I've got a bunch of data, and right now I want to make good use of it. And in Neo4j, we do this thing called pattern matching. We allow the database to say, we tell the database, find me stuff like this, right now, in a millisecond time scale, because I'm going to use this result to help empower a user to make a smart decision. And we do that using a query language called Cypher. And Cypher is like a kind of SQL for graphs. It's not as insane as SQL. It's humane. It's written by a tamed SQL DBA. Seriously, he used to be a SQL Server DBA. And his goal was to bring graphs to normal people like us. Obviously not norms, but that's probably a bit too far. So I first encountered this with Ian, actually, before we worked at Neo. And we were doing retail recommendations. We were doing a proof of concept for one of the big retailers. And you guys know how it works, right? You go through the checkout at Sainsbury's or whatever. And in the old days, what you do is you swipe your loyalty card, and then 2 weeks later, like some mail would come through your letterbox, and you'd be like, oh, that's junk mail from the supermarket, you'd immediately dump it in the bin. And that turns out was not a very good way of adjusting your buying behaviour. If you notice nowadays when you go to the supermarket, they print vouchers out at the point of sale terminal and put them in your hand. And they do that for a very good reason, because when you put something in someone's hand, that was a blank piece of paper and he looked at it. You know what? He's not a psycho. That's why most of us aren't psychos. So you don't have to hold on to it. I mean, it's going to get embarrassing now if you sit there for a minute. When you put something in someone's hand, they look at it, and it has a profound influence on their buying effect, on their buying behaviour. So if you want to know where the psychologists are that you went to university with, they're all in the supermarkets, and you thought they were doing soft science, now they're in your head more than you know. So what we learned is, put something in someone's hand, they will look at it, it will then influence their purchasing decision far, far, far more profoundly than just dropping something detached in time through their letterbox 2 weeks later. So we're going to model this in Neo4j, because Neo4j is an online transaction processing database, low latency. So it's not some kind of like Hadoop thing where you compute something and then several hours later 42 comes out. It's a good reference. Only 1 giggle for 42. I'm in an audience of developers, that's a little bit disappointing, folks. So we thought, right, we're going to model this. And so there are a few aspects to our model. There's kind of a taxonomy, so there's like a product catalogue, that's one part of our model. And the other part of our model is purchasing history for people. You can see that here. You can also see that this very much reflects my current life. So I've got some products here. So I've got alcoholic drinks, and a subtype of that is beer. And I've got Peewee Pilsner and Badger's Ale, which are both types of beer. I should also be in marketing, it turns out, and they're both members of alcoholic drinks. And then I've got this baby category, and one member of that baby category is nappies, and it's sad to say I do know specific types of nappies at this point in my life, baby dry nights. And then I've got over here, consumer electronics, game consoles, and a specific kind of game console that's in that part of the tree is Xbox 360, so I'm not Xbox One yet. And then down here, what I've got is some purchase history for a customer. I can see that this guy, Mickey Smith, happens to be a Doctor Who companion, bought an Xbox, bought some nappies, and bought something to do with beer. And this was driven by an anecdote from Walmart. And Walmart discovered that on Friday nights, if they put beer on the end cap of the nappy aisle, they sold more beer and more nappies. And that tickled us, which is why we chose this. And so what we observed is lots of people bought beer and nappies and game consoles. Kind of, because you're like busy doing baby stuff, and then when baby finally shuts his mouth in the middle of the night and goes to bed, sweet little cherub, you just want to like sit in front of the telly and like shoot stuff and have a beer. That's the model we were going for. So we stuck that in Neo4j, and that was lovely. But actually then we noticed that there's an opportunity here. So the kind of meta model that we're interested in is somebody who's a young father, so the dates change as I get older down here, to be honest, but between, say, 96 and 1972, who bought something that's something to do with beer, who bought something that's something to do with nappies, and who had not bought a game console. So, So this one, where we've got someone that's young and bought beer and nappies and game console, we can say that's a young father. That's a pattern that we say, a young father. It was also pointed out to us that this pattern also applies to just hardcore gamer. we were a young father, actually. So what we really want to do, though, is we want to influence people's buying behaviour. So if we saw young males that bought nappies and beer, but who hadn't bought an Xbox or PS3 or whatever, massive opportunity to like put a voucher in their hand, 20% off Xbox for the next 48 hours, go buy one, right? Because we know that that's a trend. So we can do that. So I can take that PowerPoint picture and I can turn it into text. It's the same graph, it's just in ASCII art now. Why are you doing this, Jim? This is very strange. Well, the next thing I'm going to do is I'm going to flatten it. So now I've flattened the graph. So it's the same graph, it's just flattened it out a bit. And this is starting to look like Neo4j cipher syntax. In fact, this is valid Neo4j cipher syntax. Because Neo4j cipher syntax is where you draw ASCII art pictures of the patterns you're interested in, using this kind of arrows and nodes convention, flatten it out, add any labels that you might want for people or categories of products, and then add the necessary Neo4j cipher clauses. In fact, now what we're saying is we want to match a certain pattern. And the pattern we want to match is when we have some person, who we'll call D, has bought something I don't care about, which is a member of some category. Where that same person, D, has bought something else that I don't care about, which is a member of another category. And introduce just a category. And where D has not bought something that's in this category, and where those categories are as follows. The first category was nappies, the second category was beer, the third category was Xbox. So what we're saying is, finding matches where D has bought something to do with beer, has bought something to do with nappies, but has not bought something to do with game consoles or Xbox in this case. So we say that's the pattern we're looking for. Go into the data set and find me those people. Whiz off into there and then return them to me. Return all of the daddies to me. And of course, you should be unsurprised to find a Doctor Who companion popped out of the database. Actually, at real time, but the 0 milliseconds counts as real time, pretty quickly. So Neo4j is designed for those kind of millisecond scale performance. Being able to print out that voucher at the point of sale terminal back in 2008, when this didn't happen, was amazing. And then we were confident we were going to go into production with this, and then we met these people called Oracle DBAs, and this went nowhere. However, things went better for us, right? Well, at least better for us being the graph community, because of these guys. Right? Along comes Facebook, saying things like social graph. Ooh, we understand that. Graph search. Ooh, we understand that. And people like Facebook graph search enables you to type into Facebook natural language. Things like, which sushi restaurants in New York City do my friends like? You could type that into Facebook graph search and it will give you an answer. What's it doing? Underneath, it's crawling the graph in real time. They don't use Neo4j, but they've got some way of doing this. And you can effectively, you're looking for a structure like this. This is me. I told you I like Eric Carmen. This is my friend Andreas and my friend Michael. And Andreas likes Sushi Zan, which is a sushi, which serves sushi. Michael likes Ice Sushi, which serves sushi, and they're both located in New York. So this is a bit of an approximation of how the graph really would be. The detail is a bit more sophisticated. You wouldn't just have one node representing New York, of course. You'd have a spatial index and artery, so you get boroughs and postcodes and streets and so on. But actually, doing this kind of Facebook graph search stuff in Neo4j is trivial. Our colleague Max DeMarzi built this in a weekend. In fact, he built something that's functionally richer than Facebook graph search in one weekend with Neo4j and some natural language processing library in Ruby. So you're able to write queries like this. If you want to write the Cypher query for this, it's trivial. So match me, where I've got some friend who likes some restaurant in some city that serves a particular cuisine, and then I constrain this to be, me has to have my name, the city location has to be New York, and the cuisine has to be sushi. Return that restaurant. Make it richer, add labels in, make it more readable, make it seeped in the domain. So match a person, which is me, who has a friend, which is also a person, who likes something which is a tagged restaurant, which is located in some place, which serves some cuisine, and constrain it to me in New York and sushi. And then even make it more compact. Match some person with the name Jim, who has some friend of another person who likes a restaurant, where that restaurant is located in New York, which serves sushi. Give me the restaurant. This is not rocket science. Cypher makes doing this kind of Facebook graph search stuff trivial. It's really, really simple to get going. We teach Cypher to people in Breakout, and then you pretty much are competent in Cypher after that to do this kind of stuff. Under the covers, how come this scales?
Sorry, I have to go. I've got to pick up my daughter, but
That's a
I'd
brilliant
love to
excuse.
stay, but it's very interesting.
Yeah, now we have to make the gag you start a trend because you're off soon as well. And then this is a trial closure of exit for me. So, how on earth does this scale? Because Facebook work at like zillions of bytes of data, right? And it turns out that graphs scale really well because your query latency is proportional to how much of the graph you traverse. It is not proportional to how much data is in the database. So if you've got a Neo4j database and you've got 1 billion nodes in it and 7 billion relationships, effectively harvested the Facebook social graph, and you wanted to run this query, would it scan? Would it do a Cartesian product of all those nodes and relationships? Hell no. A good graph database simply does pointer chasing. So actually, when you're doing a Facebook graph search, it's just doing pointer chasing to find out the next relationships, the next nodes we should go to. So the query latency is proportional to how much of the graph you choose to explore. Which means this stuff is great, absolutely fantastic for doing real-time work, for doing online transaction processing workloads. Sure, we can do OLAP stuff, we can see how we can iteratively move, iteratively change the graph and do some, many hours of computation and predict how the graph may evolve. But this stuff is absolutely phenomenal for OLTP stuff as well. In fact, the T is particularly important because Neo4j is ACID transactional because we take your data seriously. In fact, Neo4j grew up in Sweden originally, and We all know what kind of cars come from Sweden, right? The safest, most boring cars. And we are the safest, most boring database in the operational sense, or even though the data model is phenomenal. So, demo. Let's pray that the demo gods are with me. I want to show you how you can do real-time analytics. Let me mirror my screen. I will optimize it. I'm going to sit down for this so I can type a bit better. So, on my laptop, I've got Neo4j running, and it's empty at the moment. Wow, they've given us a really low resolution, screen. This is going to be fun. And I know it's empty because I can say match everything in the database and return it all, and it comes back nothing in there. Right, so it's an empty database. Now, I'm going to add because everyone suffers fat fingers when they are trying to type these demos in front of an intimidating audience that's staring at them and expecting them to do good things. Forgive me, but I've got these snippets of code that I'm going to use in my sidebar here. So I'm going to populate my database with a simple retail data set. And all this has is a few products. So you can see I've got bread and butter and toothpaste for some reason. I wrote this on the aeroplane, you know, it's a bit random. And I've also got some other data that says that things like bread is complementary to butter. So, you know, if someone buys bread, we could perhaps recommend they also buy butter. If someone buys toothpaste, I think I end up recommending they also buy tagliatelle, but that's some weird things. And I've got down here as well, I've got some baskets. So I've got some customer baskets that have been purchased, some that have been saved, some that are current. And I've got a bunch of customers. And Alice and Bob and Charlie. And right at the bottom here, I've got some social network. So you can see in Neo4j, creating data is easy. You just draw the shape of the graph that you want to store in ASCII art and ask the database to create it. So you can see here I've got great Charlie, the node representing Charlie has an outgoing friend relationship to the node representing Dora. And thankfully for Charlie, Dora has an outgoing friend relationship to Charlie. So Charlie is friend with Dora, Dora is friend with Charlie. Because it turns out that not everyone you follow on Twitter follows you back, right? It's not a symmetric relationship. So if I go ahead and run that, I've now got an enormous data set consisting of 22 items. This is big data at work here. 53 relationships, though. I mean, that's a phenomenal achievement. If I get the whole database back now, you'll see I've got this kind of thing going on. See, somewhere in this complicated nest, you can see products, you can see customers, you can see baskets, and that's fine. Capture. You can see basket IDs and so on. I put that as name and color them yellow. There we go. So you can see customers, you can see baskets, and you can see products. Yeah, kind of it's a bit messy the way it's presented, but I hope to make sense of it. So, what might you do next? What might be something the supermarket wants to know? Well, what about just the top 5 things that we're selling? Yeah. From a supermarket's point of view, that might be useful, be able to make sure that your supply chains are aligned for that. So let's take a look. How does it look here? So we've got this match clause. And match is saying settle a pattern. And we say, okay, I'm interested in a customer who bought something in a basket which was tagged as product. And I want to, when you find that pattern, so this of course is a graph match, we're looking for that whole path. Customer, basket, product. When you find it, return the product, return the count of the product, and order by the count of the product in a descending fashion, and limit to the top 5. So this is going to give us the top 5 most frequently purchased, hopefully it's going to give us the top 5 most frequently purchased products. When we run it, we get these guys. Thank you. Little premature, boys and girls, but okay, when we finish, don't just applaud, just go, yeah, fuck yeah! See if we can give as good as we got there. So, you've given us a graphic format there, but actually I think this one is better in a columnar format. So the top 5 products are whole milk, unsliced loaf, tagliatelle, butter and tea bags. World's weirdest supermarket, or world's weirdest customers anyway. Banter them on the way out for me at least. Alright, so that's fine. However, this really isn't very personalised, right? This is all like the supermarket's view. It's like the supermarket's selling a lot of unsliced loaves and tagliatelle, great. But it's not going to help you change an individual's buying behaviour. So we need to somehow focus this around one of the individuals. So let's do that, right? Let's look at what Alice buys a lot of. So what are Alice's top 5 products? And in this case, all we've done is focus the graph around Alice. So we've included the customer, the specific customer that we're interested in is Alice. And again, it's the same pattern other than that. It's where Alice bought a basket and where a product was in that basket, returned the product, and ordered by in a descending fashion by counted product. If we run this, we're going to get some different things. It turns out that Alice's top 5 are actually only 3. She's only bought 3 things. She's bought butter, bread, and toothpaste, which makes some sense. I guess you want to eat some bread and butter and then brush your teeth. Yeah, that's great. But so that's fine. We now know a little bit. We've got a little bit of insight into Alice and how might we act on that. Well, remember when we built the data set, some of the data, some of the connectivity we put in there was about complementary products, and we said that toothpaste was complementary to toothbrush. So perhaps now, if we ever saw that someone had bought toothpaste and had not bought a toothbrush, we should recommend, hey, you should buy a toothbrush, because like doing it on your finger is not terribly effective. Dentists recommend more than that, it turns out. Okay, so let's amp it up a bit. Now, there's not only that, but then the next one. It turns out, and I'm sorry to accuse you wonderful people of this, but we're all the same. We are all proper Joneses. You did not need the iPhone 5S. You did not want it, you did not desire it, until that other guy in your office came in with it, and you were like, ah. And then suddenly, you're like, oh, I need an iPhone 5S. And somehow, your perfectly serviceable iPhone 4S developed a screen fault. Didn't it, Mrs. Weber? Anyway, what we actually want to do, one of the most powerful things you can do, is just tell people to buy what their friends or social peers are buying, and they will fall to that peer pressure every single time. So what if Alice, what if we didn't just tell her about complementary products, which we'll get to, but what if we told her about what her friends and her friends of friends are buying? Because that's going to put pressure on her to kind of buy those products. I mean, you know, if all of her friends are buying tagliatelle, she does not want to be the weirdo who's left without any tagliatelle when the friends come round. I really wish I picked beer for that, because that seems much more sensible. Hey, come round my house, do you want some tagliatelle? No. Anyway, so let's have a look at that. This is a much more interesting query, I think. So let's have a look at friends and friends of friends. So this time, again, we're starting with Alice. It's Alice's friends and friends of friends. So, but part of the graph we're interested in is, look at this syntax here, we're following Alice's outgoing relationships from Alice, labelled friend, at depth 1, Alice's immediate friends, or at depth 2, Alice's friends of friends, because that's also quite a kind of an influential peer network, where those friends are also customers. We're putting a constraint in here, where customer and friend are not the same, right? Because we don't want, because of course, friend of friend could be you. So Ian is my friend, and Ian hopefully has a friend relationship back to me, but I don't want that friend of friend to be me. So I'm ruling myself, or in this case, I'm ruling Alice out of the query. And I'm saying, take that social network, that friend stuff, and we're going to pipe that into the second part of the query. With is kind of is how we kind of chain together segments of a query in Neo4j. And now we're going to match the pattern where a friend has bought something in a basket, which was some product that was in a basket. And then we are going to return products, we're going to order by the count of products and limit it to 5. So it's not Alice's purchases now, it's her peer group's purchases. And when we run it, we find that whole milk is overwhelmingly the most popular, followed by unsliced loaf. Tagliatelle is in there, and Alice does not have tagliatelle. She is weird, and her friends and friends of friends will ostracize her for that. And then finally, some butter. So you can start to use, this is a simple example, right? Friends of friends. But things like YouGov, you know, the kind of government sentiment site, they build on Neo4j. And a few years ago, we were sharing an office with them. They were building a product to gather sentiment. And one of the analysts that was working on the project was like a really, really, really smart analyst. And she says, do you want to see what we've done? I'm like, yeah, because you're building on Neo4j, and this is all what we've done. So she's like, okay, so tell me your age and your postcode. And I'm like, what? Really? Okay, yeah, whatever, 37. That wasn't the time, it was a while ago. He's like, okay, what postcode is it? SE22. And like, what else do you need to know? She's like, no, nothing else. Well, what do you mean? Well, she's like, well, you're 37, you live in SE22, you are married with 1 or 2 children, you read The Guardian, you drive a Toyota Prius or equivalent, and then she continued to list this set of extraordinarily boring facts about me. And it was incredible. It's like, yay, graph theory again. But what it meant was this analyst just knew how undesirable I was as a human being, how dull and predictable and generally a waste of carbon I am. And it was horrible, it was horrible. It didn't help that she was like this herself, this super smart, super attractive lady, like confident, and we were all a little bit kind of scared of her anyway. And then she just, yeah, you're so boring. I would never consider you as a possible mate, which was the undertone for all of this. Crushing. Anyway, so the point being, you don't have to stop just friend of friends, but you could bring in things like postcode, social demographic, party political loyalties or car that they drive, and you can bring all of these dimensions of data into the recommendation to make it more refined. And your restriction is how much of the graph do you want to explore, because that will govern your query latency. If you can afford hundreds of milliseconds, explore more of the graph, and you'll get a better recommendation. If you can only explore if you can afford tens of milliseconds, then choose to explore the most important parts of the graph and make sure that you're containing your latency. And then finally, what about recommendations for complementary products? God only knows, anyone that works for a supermarket, when I do my online shopping, it's just like, and they substitute shit. Right? I order unsmoked bacon, don't have any smoked bacon. No! I get angry about this, right? Because it's such a trivial data problem. If I am buying, like, Diet Coke, the important thing is not Coke, the important thing is diet. If you don't have any, give me Diet Pepsi, right? Anyway, same kind of things going on here with, like, complementary products. You can, if you've got a handle on some things that people are buying, you can make positive suggestions about what they should also buy. And of course, supermarket people know, supermarket metadata people, is that wrong? Probably is wrong, isn't it? There's some poor people who have to just comb through a taxonomy of like, well, cheddar is a kind of cheese, blah, 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 blah. What job? But they know that some things are complementary to one another. Bread and butter, toothpaste and toothbrushes, blah, blah, blah. And so actually, if you can put those cross connections into your taxonomy, you can start to take advantage of them to upsell, or at least additionally sell people items. So it's not just people who bought butter also bought bread, but it's actually, we know that bread and butter go well together. You'd be well served to get some. So we can run that query. So again, we're going to look at Alice. And we're going to look at what she's currently got in her basket. So this is Alice's current basket, and we're looking at some products in that basket, and we want products which have an outgoing complementary to relationship to some other product, and then we're just going to return complementary ones. So look at a basket, identify complementary products, and put them in front of the user. You bought, give me a complimentary, I've gone blank now. You bought tomatoes, you might also like to buy basil or salt, because they go brilliantly with tomatoes. So when we run this, please don't let it get tagliatelle. We find, all right, based on what Alice has got in her basket, she should be recommended that she buys butter, sliced bread, or unsliced bread, because they are complementary things. So it's kind of an upsell opportunity just based on this simple connected knowledge that things go well together. Wow, that worked. So now you know how, Tesco Club Card and all those things work, albeit in the small.
Can you ask it to show you whether no relationships?
Can I ask it to show whether
relationships are not there?
Yes, so let me, in fact, the easiest thing I can do, so I don't have to do any typing, which could go terribly slow, would be to refer you back here, and you'd use this syntax. So remember what it was, I want to buy an Xbox, I want nappies and beer, and explicitly not an Xbox in there.
Can you just learn these patterns? Or do you have to sit down and figure them out?
Yeah, so for something like a retail data set, it turns out they're a domain specialist because it's a complex domain. But you've got a choice. So sometimes you're going to have humans who are poring over subsets of the data, and they're going to be looking for opportunities for upsell or taxonomy or whatever. But you can also bring into play things like machine learning to actually kind of comb over your data set and look for these kind of opportunities too. That's way out of my area of expertise, but a coupling of graphs and machine learning is a very reasonable thing to do. Oh, wow, this actually did go on for 90 minutes. So what's Neo4j good for? Neo4j always started off as add social to your website, and that served us pretty well for a while, but I'm pretty confident now to say that graph databases, Neo4j, are a general purpose database. Where you might consider plugging in a SQL database today, tomorrow you should absolutely consider plugging in Neo4j. Operationally, it's the same as SQL or Oracle, it's a transactional database, but the data model is kick-ass, and the query language is super lovely and humane. You will be proficient and feel powerful with it very quickly. And we've seen it deployed in disparate domains. We've seen it in data center management, in mobile phone mast placement, we've seen it in healthcare, we've seen it in accounting, we've seen it in pricing for investment banks, we've seen it in access control, we've seen it in loads and loads of different things. And every time we bump into more people using Neo4j, they're like, oh, we're doing it for blah, blah, blah. It's like, oh yeah, that's a graph problem as well. Pretty much everything is a graph problem, because everything's connected and graphs are all about managing connected data. And Neo4j, even though it's got this absolutely infuriating 4j bit at the end, don't worry if you're not a Java person, Neo4j is just a database, and it's uncontroversial, because even though you might think your DBAs are conservative, they are nowhere near as conservative as eBay, or HP, or Cisco, or anything that's written in German. I mean, that is the epitome of conservatism right there. The largest parcel network in Europe runs on Neo4j, doing real-time routing for 3,000 items a second. And it was brilliant. Ian was at a conference where one of the guys who built it was talking about it, and an Oracle DBA got up to argue, and the guy said something along the lines of, why you just made that ridiculous point? My parcel routing network has already routed 20,000 parcels, sit down, and we just So Neo4j is not controversial anymore. It's weird technology when you first come to it, but a lot of very conservative buyers have bought it and made good of it, and also a lot of exciting startup-y things are into it, so it's a real good mixture of people using the technology for a wide range of things. I mean, when the Fortune 1 company uses Neo4j, that's Walmart by the way, right? And this Fortune 2000, which has 1,999 more of them, that's Fortune 1, they're Neo4j users. You have no excuse. These guys are like super conservative, super price sensitive, like super insane amounts of data. They use Neo4j. eBay uses it, I mean, for heaven's sake, it's uncontroversial right about now, because it's 2014. There is available to you lovely people a free O'Reilly book in the paper format. Come and talk to us at the Neo4j stand downstairs. If you haven't already, we've got loads of copies to give out. And we'd like to give them out because we don't want to carry them back to the office because it's all the way over by London Bridge, as you now know. Or if you prefer an ebook version, if you go to graphdatabases.com, you can download exactly the same full ebook version for free there. You just have to give us your email address and say, I'm interested in things about the Graph Databases book. So that's all I've got, apart from a meme to finish. Thank you for listening. I'm happy to take some questions while we have a few minutes left. I like that stunt. Someone just pelted me with graphs for 90 minutes and now you want me to say things.
What's the transition like from relational to...
For me?
For existing data set, so you want to move on to...
Yeah, so so we've had people who have just kind of exported and then imported. It's the wrong thing to do because you effectively take all of your row, you do a mega join, and you take each row and you put it as a node in the database, in the Neo database. That's wrong. What you have to do is you have to be able to translate the model. So you have a model in your relational database. You have to think about how to recast that as a graph model, right? So you're not going to have tables and rows anymore. You're going to have nodes that are interconnected. You have to figure out the mapping. Once you figured out the mapping, there are a bunch of mechanical tools that will help you do the kind of physical, high volume export and import. But the cranial work is in figuring out how do I go from this model that I have in my relational store to the model I want in my graph. And I think if you're new to graphs, the first thing to do is learn the graph thing. So that you can have okay, now I understand graphs. I can figure out how I can map from the concepts I have in my relational store into an idiomatic graph store. Because what you don't want to do is create an un-idiomatic graph store, because if you do, the queries are going to suck. They're going to take seconds rather than milliseconds. So learn graphs, step one. Something, 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 profit.
So previously worked with ontologies and things like that. So it's very something, but our with
to real graphs.
And I was always slammed by traditional database people telling me that there's too verbose. And they do have a point. But like looking at sort of Cypher, and you're working at the create schema and the same sort of velocity problem.
It's not as verbose as RDF, that's for sure.
No. But you still, I mean, it's far more than a table.
No, actually, if you look at the no. So I actually did some slides because I didn't want to get into a SQL flame war. So here we go. He's going to try. This is some SQL for just finding flights from JFK, so from SFO to JFK. Actually, we couldn't do it. We actually had to get one of our interns to write it for us because it was so complicated. The equivalent cipher code is that. It's way less verbose.
I wasn't talking about the query construction. I was talking more about sort of say, when I had to do it, if I wanted to say that you lived in S22, I'd have to say you lived in S22.
Yeah.
If I have to say that I lived, I have to say also say that I
Yes,
lived
you
in
do.
S22.
Absolutely. Yeah.
So I repeat, essentially, I've got 3 lines.
You have? That's okay, because all you're doing there is pouring facts into the database, right? Is that particularly verbose? No, because if you had a load of people that lived in SE22, you do a CSV import, right? Done deal, then the data's in the database, and then you hit those people when you query for SE22. So yeah, I mean, you've got to get the data in. You can't. I'm not going to give you some optimized binary format for that because that'd be confusing and terrible. But you do have the ability to. So if you don't like the Cypher stuff for that, you have the opportunity to do a CSV import, or you can drop down to one of the programmatic APIs and program it in Python or Java or whatever you choose. And then you can, for those kind of bulk import tasks, you've got options at your disposal. Cypher is lovely. It should be your first choice. Anyway, so.
Does it do routing?
Yeah, so you can do things like shortest paths and all shortest paths. There's an A-star algorithm and Dijkstra's algorithms built in. And if those aren't enough for you, we integrate really well with the Jung library, so you can actually pull arbitrary graph algorithms out. And of course, there's a programmatic API. So if you've got some specific graph algorithm that you need to fine tune, you can always code that in Python, Java, blah, 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 blah.
Yeah. How do you manage the actual data that's persistent on the disk?
Right, yeah, that's a pretty good technical question. So every node, every relationship, every property is stored on disk. Those particular, I want to re-emphasize that, relationships are on disk. Relationships and properties are fixed length records, which means that when we're traversing around, that's those store files, we just need to compute and offset it. We know how big they are, we know the ID of the thing you're currently on and the ID of the thing you want to traverse to, therefore we can compute in order 1 where you're going next. So actually, those store files are designed expressly for traversal performance. Then you've got property files where we store the key value data. Those things are more variable length records. And that's where when you found the right nodes that you're looking for, then you pull the variable length data out. Which is why in Neo4j idiomatic search, we tend to ask you, use the structure. Find where you want to go by traversing the graph, and then when you reach your goals, then pull the data out. If you can avoid it, don't check properties as you go along the way, because you'll be doing another IOP to another store file. But if you do an idiomatic search, which is use the structure and then pull your data out, it goes like grease lightning because it's just doing pointer chasing. And if you want to break out your hex editor when you get home, you'll be able to see those records represented on disk in your database. So you'll see those relationships, properties, and you'll see some schemas and index stuff in there as well.
I imagine it probably works quite well with XML exports, doesn't it?
Well, XML's a tree, yeah. So if you wanted to take like a big blob of XML and kind of represent that as a tree in the database, absolutely. Yeah, so you could import that, you can imagine it's a fairly simple transform of your XML to Cypher, and then you'd be able to Cypher query your tree. So yes. And then of course, when you've got it in Neo, you're not restricted to a tree format that XML is. You can start to put cross linkages in and make it into a true graph. If that was a kind of question, can I replace mark logic, which I hate, with Neo4j, which I love? Yes, absolutely. Mark logic. Anymore? No, okay, well, thanks, so it's been lovely spending time with you. And we go downstairs for beers, I think, now. That's a lovely end. No one scream fuck yeah at those guys.